What you see here is a SMPTE 291M Type 2 packet. That packet is identified by the DID and SID as a KLV metadata packet. The length of that packet is restricted to the data count, which defines the total length of the user data word, which can be up to 255 bytes. When it's KLV, there's actually only 235 bytes, or up to 235 bytes remaining, as the message ID, the program segment counter bytes, the key, which is 16, and the length, which is 1, totaling 20 bytes, are consumed inside the user data word space. To learn more about metadata, where it is in the frame and the structures, take a look at our What is Metadata presentation, and you can learn a lot more information. Inside that presentation, we refer to the means in which to actually insert metadata into each video frame, how that metadata can be unique, how to extract it, that it can be overlaid, and some of the other things that our equipment will let you do, and others in the future will let you do, I'm sure. In this presentation, we're going to tell you how to make your own metadata key to serve your particular needs for a test or other data that you're trying to collect that might be unique to your needs. All KLV metadata fits inside a user data word of a KLV packet. The key is assigned, and that key can be put into a dictionary, which SMPTE and both MISB have as dictionaries, or your own. It's a 16-byte word, which then uniquely identifies this particular structure and what its content structure is. The length says how many bytes is the payload. We refer to the payload as the KLV value itself. The value can be 1 to 235 bytes, and that is identified with the length byte. Up to 235 bytes can be in the payload. And the payload is memory space. Up to 235 bytes, which you can store ASCII text, integers, signed numbers, scaled numbers, binary fields, whatever you choose, and however you choose to organize this 235 bytes of memory space. As I said, it doesn't have to be 235 bytes. It can be as simple as 1 byte. In fact, the MISB timestamp, like we revealed in the previous tech brief, was only 9 bytes, 1 status byte, and 8 bytes of microseconds since January 1st, 1970. In this example, we're actually showing a real key used by the UMA Proving Ground. They created on our tool called the Key Template. The Key Template allows you to make labels for every field. The Key Template automatically assigns the field number, and in here you get to decide what the offset into the 235 bytes is for this particular value. In this case, temperature was 25 bytes into the memory space, and it had an input length of 6 bytes, and it was ASCII format. And it's just the way the data logger that we received data from provided that data and was parsed with 6 bytes for the temperature. So this tool then will let you define that memory space in both its offsets and how many bytes to use, and what kind of data it is. The Key Template keeps track of how many bytes are in the key, how many fields there are in the key, and then you can assign a number to it, which is your unique number. And as long as you stay away from a previously registered key, this acts just the same as in Ethernet. If a data packet is running around your network, but it's not addressed to you, you ignore it. You don't process that data. Similarly, if you have a packet that's properly structured, it won't bother any of the equipment that is used to seeing metadata packets. When it sees a KLV metadata packet, it will extract that, look at the key, and say, this is not my key, I don't care about it, and it will not process it. So it's all interoperable with all of the commercial gear that's there, provided you stay away from registered keys. Several years ago, ITS began developing a comprehensive toolset that would allow you to create custom keys and structures that fit in the metadata KLV packets. The purpose is to be able to capture data of your design and your needs, synchronized with incoming video all in real time. So now you would have a data sample related to the image sample, a data sample related to the image sample, a data sample related to the image sample, which allows you to see the performance of objects and both visually and with the related data that either stimulates them or measures their response to them. The key template itself is an Excel spreadsheet. We created this to enable you to build the structure of the payload in a key and carry with it labels that make sense of what that data is to a human, and also define the offsets and byte lengths of each of the data types that you choose for insertion into the key. The system also allows you to define the key number. The key number, you notice, is quite long. It's 32 hex characters. That is 16 bytes. 16 bytes is the SINFI spec for how long a key must be. The only caution we give you is to stay away from registered key numbers. The key numbers, in general, start with an 06. If you take a look at the SINFI dictionary in RP210, or you take a look at the MISB dictionary in 0807, you'll see that they all start with 06. The benefit there then is if you stay away from 06, chances are you have a key that none of the equipment downstream will recognize except for our equipment or others that may become aware of that particular key number. With that key number, systems can look up the structure and then be able to use the data either for display or analysis or extraction. Once you have that key number assigned, our spreadsheet actually will give you indicators, as this box in F1 would show, or in H1 would show. When you have a green here and you have an OK there, you have 32 characters and they're all hex. It doesn't check that it isn't an 06, but it does check those things. The key template then is constructed itself of a field name, a field number which is assigned by the spreadsheet itself, a start byte which you assign, the padding before that byte is calculated by the spreadsheet, the format that you assign, and we'll talk about the formats in a little bit, the input length, meaning how many bytes is this particular line of data. How many bytes is that? This is the range length that's allowed for this data type that you've selected. And if they are scaled values that you've selected, it will actually show you, like you see down here, a scale factor that you can put on that when those number of bytes are full of ones. This field shows you the decimal places for display time, where to place the decimal point at the time it's displayed. You see some are zeros, some are sixes, and so on. That all defines how to display the data. It doesn't have any effect on how it's recorded or inserted. The display model in the spreadsheet gives you an idea about how a full-scale data would, as you defined it, would be displayed on our equipment at the time of extraction. an overlay. The resolution shows you what the value is of the first byte, the first bit of the first byte. This budget timing is kind of a reference. It's to give you an idea that if you wanted to show all of these fields, and that's what plan to show is about, if you wanted to show all of these fields in real time, meaning that at a 60 frame a second video rate, I want to show all of these fields at once and be able to keep up with the data. This gives you an idea whether it would actually work or not, whether we have enough processing time in our equipment to capture a full packet of all of this data, formatted the way it needs to be formatted, create the strings to put them in overlay, whether you can keep up with it or not. And that's what that's about. So to begin, after you've assigned a key number, you can take the first field, give it a label. The field number is assigned. In this case, you see it's 4 because there's some that you're not seeing here. You have the start byte. In this case, 12 bytes into the total of 150 bytes that is in this key is where this UINZL3, and I'll explain what that is a little bit, labeled field is. It's a unsigned integer, and it's 3 bytes long in this particular case. The length range for an unsigned integer can be 1 to 4 bytes. That's what this indicates. And it's not scaled, so this is grayed out. It says there's no decimal places shown, so an unscaled integer of 3 bytes long would have a maximum value of 16777,215 and with a resolution of 1 for the first bit of the first byte. So that's what this spreadsheet will do and help you construct and manage the display at the time of extraction of what this data looks like. The only thing that really ends up in the metadata pack itself is the bytes. This is all defining the structure of those bytes so you know how to extract and overlay them as needed. The spreadsheet supports up to 64 different fields of data, so you can have a pretty comprehensive key. And our equipment generally supports 2 KLV packets, so you can actually define with 2 of these keys 70 bytes of data that's collected in synchronism with the video sampled on each video vertical sync equivalent. This particular sample that you're seeing is our own internal test key. It's a key that will use every format that we support to be sure that our math is happening correctly and that all of the supported formats are properly transferred to the code that's in the FPGAs for insertion and extraction and overlay. The reference information tab in the key template gives you an idea of things that we call internal fields. Internal fields is information that we have already inside the unit. For example, if it is a GPS synchronized unit, and nearly all the HD equipment is, we have access to the data from the GPS receiver that tells us the latitude, the longitude, the height, and the time. And the time is put in the microsecond timestamp, but you may want to show the current latitude, longitude, and altitude at the time a particular image was captured. In that particular case, you can do that, and by telling our system use an internal field and formatting it the way we specify here as the byte length, and how many decimal places you should define the output and what the max value might be. In this particular case, it's a latitude, so those will all fit a latitude definition. You can see that various equipment has other features in it. For example, you can capture the time zone offset at the time, which is not really a dynamic value, but a value. The time sync source, so you know that it's iRig or GPS, and in some equipment NTP. The video format that was being recorded at the time or captured at the time with this video, so you'll know what you have. The frame rate, the IP address of the equipment that was doing the insertion. If you're using our camera sync features, the camera sync delays, the timestamp offsets associated with the camera sync delays, what event it was capturing the timestamp, and there's a special interface for a KTM that's available in our 6055 product, and we can capture the azimuth, elevation, and range of the KTM with that interface in those products, and what the range units were. So all of those fields are available depending on the equipment, and it's shown here what can be captured in what equipment, shown in this area. The Reference Information tab now helps you understand how to select the data type. You can see here that the data types that we offer are binary. It's a value that we do nothing with, but they can be 1 to 235 bytes long, so you can carry even classified data, perhaps. That's a cipher in binary form, and put it up in the metadata and move it across a network. ASCII data, and ASCII data obviously have characters, so it has to be a printable character, and it can be up to 235 bytes long. But then you also have unsigned non-leading zeros, unsigned with leading zeros, and the non-leading zero with leading zeros is a display specification, how you want to display that value. But the unsigned integers can be 4 bytes long, and you can see what their max values might be as you go through them. It gives you a description of what each one is. You also have signed integers. Those can be 4 bytes long at half the maximum value lengths. And then you have signed and unsigned max. Now the max indicates that the value is scaled. The scale is relative to the full scale value of the bytes, not the source. So if you have 255 bits, meaning a 1 byte signed integer, you have 127 bits of value. So at 127, you can assign that to some value like 300. It can be any numerical value, and the value will be the current value of the number of bits that come in on that particular variable will be scaled to that accordingly. So you can use this as a way to adjust the display of data. It has no effect whatsoever on what's actually put up in the metadata. This is all display time kind of information, so that, and its definition, so that someone else that's reading your data can then use this along with the byte length and offsets to decide how to interpret the data that's been captured up in the metadata packet. We also have a single precision and double precision value that we can capture. The single is a 32-bit value, and the double precision is a 64-bit value, but only 8 bits of it. Excuse me, 8 bytes of it. And the full-scale maxes are shown. Then the UI-F is actually a custom interface that we designed to be compatible with our existing KTM interface that works in the 6055Cs. These are pretty broad use at Yuma Proving Ground and other places. for capturing the camera mount data. So to go through this once more, you assign a key, as shown here, and assign a field name if you choose. It can be anything that you wish it to be. You assign a start byte, you assign a data type, you assign an input length, how many bytes that data type is going to be. The spreadsheet key template gives you a specification of the maximum number of bytes it can be. So in this case, a scaled unsigned integer can be 1 to 3 bytes long. In this case, since it's scaled, we're saying that at full scale it's 100, and it will have 0 decimal places. So the display model then shows that when it is full scale, 2 bytes of full scale unsigned, it will display 99.99695 with a single bit resolution of 0.00153. You can go through this whole design then and build a key payload with up to 64 fields using this template. Once you've created this template, you can save the resulting file as a CSV file. Now you probably want to keep the Excel form of it as well and save the CSV file separately. The CSV file then is used by all of the ITS equipment for inserting metadata packets and display those metadata packets so it knows how to parse it. It's used by some input software we have, we call the data concentrator. It's used by the key test that we'll describe to you in a little bit. It's used by key read that we'll describe to you in a little bit. And it's also used by the download video program, which we'll describe to you in a little bit. There's also an open action right now to be able to interpret the CSV file inside of TrackEye. It isn't done yet at the time of this recording, but it is an open action for them to do, which would be very handy for you because then you can automate the collection of data from the data acquisition system all the way through the recording system, the playback, and then transfer that video with metadata to TrackEye and have TrackEye ingest this with the key and know how to interpret the data that's been captured. So part of this comprehensive tool set is how to get data into the payload that you just created with Key Template. We have a piece of software we call Data Concentrator as one way to do it, where you can have data coming in from multiple devices into a PC, and with the Data Concentrator, tell the Data Concentrator where the source is coming from. It could be a COM port, it could be another Ethernet port, and bring that data in, interpret it, parse it, and map it to the fields you just created with the Key Template. And once that's in that structure in the payload, that software then will put it in an envelope that has some ITS insertion commands that will then tell it when and what what key to put the data capture in on the video that's coming in. The beauty is that the data can be coming to us as payload packets much faster than the frame rate, so that what you have is data that's very close to the start of each frame, as our equipment then subsamples the data on the start of active video on the first line of every frame. So it's a consistent place regardless of the format. We know of some others that will put the timestamp, for example, not on the first line, but actually when the vertical sync, as SMPTE defines it, is displayed, decoded. The problem with that is that the number of lines at the bottom of a video frame is a variable depending on whether it's a 720, a 1080, or even a 4K frame. There are different buffer lines at the bottom, so that actually changes the time from the top of the frame. So we always capture on the first line of the new frame that time and then insert it in line 9. Right after that, we'll put your payload packets that have been defined in with the key template. And so as this data comes in asynchronously, on every vertical sync point, we capture the last full packet of payload and insert it into the metadata as a KLV packet defined by SYNTIC. So each frame then will have unique data that's synchronized on its insertion time. So looking overall then, what you see is some kind of a sensor system. In this case, we're showing YPG used this with a Campbell data logger. That data logger input came through a serial port into a PC, their workstation, running our data concentrator software, which is one of our software tools. The data concentrator was told, it was specified to look at the serial port that the Campbell was looked at, was coming in on. The Campbell had a 30-byte record that it was sending to us, and we were able to define, and the customers actually defined for us, which they could do themselves. This tool lets you define it yourself to say that this particular source, so many bytes in is this data, so many bytes in is this data, so many bytes in is this data, and as a result then we parsed the incoming 300-byte record down to the bytes of interest, and then you can map those bytes as they come in to the fields you've defined with the key template. And what is showing here is actually after the key template's been imported into the data concentrator from its CSV file, you see the labels of all the data, and you see the result here that as the Campbell was sending data in, the data concentrator was intercepting those 300-byte records, parsing them, and then populating them in the fields as you define the structure for the key. When you've done that, the data concentrator can then be instructed to send packets of data at some rate, up to 200 times a second, and wrap those in ITS insertion commands, and they can go into our 6055, our 6980, our 6041, and all of those are video inserters, pass-through devices. And they can also go to our 6520 uncompressed video recorder. In any of those cases, what will happen is at the time of capture, the video will come in from some camera asynchronously and go into our insertion unit. The payload packets will come in asynchronously at a higher rate, hopefully, and the data will then be inserted into the frame as each start of the frame up here in the corners begins. We'll sample this data packet, the last packet that we had, and put them into the video. So your output video then is the same video you brought in, uncompressed, unmodified in the image area, but up in the data space, and the bank data space specifically, we put KLV packets, possibly 2 additional packets from the microsecond timestamp. So you can have 1 microsecond timestamp or up to 2 KLV packets. So you have 3 packets up there, and that data has all been captured and synchronized with the video. On the decode side, we have other software to support that. What's showing here is a sample of the recorder that I mentioned earlier. The recorder, the 6520, records either to a volatile memory only or to a volatile memory as an event and then saves to the SSD, or will write all to just the SSD. And with the SSD in place, with a 1 terabyte, we can get about 43 minutes of 1080p 60 3G video. With a 2 terabyte drive, we can get 88 minutes. saved as uncompressed real-time video, and we can be putting metadata in all as we go. You can also have 512 different clips, all with their own unique metadata recorded and synchronized with the video that came in. Using the data concentrator, we could have actually multiple sources, not just a single, as I showed earlier. You can have a data acquisition system. You might have sensors directly connected to a PC, and you might have mount data coming in. And that actually can be defined all inside the data concentrator software to tell it which ports each of those data sources are coming in, what a record looked like, how to parse that record, and then to take the parsings and map them to the fields you've defined in the key. And it will then update the packets based upon the update rate that you choose and send those out to the recorder. And it will, just like a 6055, as video comes in, stuff those packets into line 9 right after the microsecond timestamp and record it. We'll also, at playback time, when you get playback, you get the uncompressed video just the way it came from the camera, but with the metadata loaded into it. And at playback time, the recorder actually has a decode channel in it. It's a full inserter on the playback side. So you can give it the definition from the key template CSV file and tell it to extract the metadata, parse it, create strings, and overlay it at particular places on the frame that you choose. So now you have a complete system where you can put the data in, you can record the data, save the data, replay the data, extract the data, and overlay it for analysis and review. And this is a block diagram showing the same thing for just an inserter. On the playback side, now you have something very interesting in that at playback, what's been captured already by the recorder can be played back, and it has the metadata captured at record time synchronized to each video frame. The output, as I said earlier, of the recorder is a full inserter, and you can put the inserter in read metadata mode, give it the key template information through the CSV file, and you can actually specify to overlay the data as it's played back. This does not affect the video frames as they were recorded, but simply shows you the data, like I'm showing here, shows you the data at a place that you choose. It's a real value to this because if you were burning it in, as has been the case for most of the video world from analog video days 30 years ago, if you burn it in and you pick a color that is the same background as the same color as your background, for example, you choose yellow and you scan out to the desert in high noon, you're not going to see that yellow very well. Well, the good news is now the overlay is created in real time at playback, so you can change the color. You can also, if you burned it in and the text happens to cover up something that's going on that you wish you could see, again, the good news is the frames are unblemished by any overlay, and you can move that overlay that you want to see the data, move it out of the way of something that happened. So you have a lot more control of how you see the metadata, or how you see the data you've collected, and have unblemished frames to view at any time. The other things you can do with this is you can send this information, the configuration, with one of our configuration utilities for the 6520, and there's one for the 6055 and the 6041, 6980 set as well. You import the CSV file to them, and now it knows how to extract that data and take it out and bring it to a file that we call a PFD file, which has all of the sensor samples in it. And that PFD file then can be used with another element of our toolset, key read. Again, bring the CSV file that defined the key into this. It reconstructs the key with all of its labels, it can read the PFD file, and for every record, meaning every frame that you captured data, you will see a display of the data in human readable form for every frame. And then once you have that, key read can extract that data and save it as a CSV file. What's unique about this, it isn't just the data then, the timestamps are also captured with it, and the key that was used for each field. So you can take a look at the key, you can see the time it was captured, and then all of the data that was captured with that particular frame. And every record then is a frame of the data. Thank you for listening. I hope this was informative.